On a wave-swept rock 13 kilometers off Cornwall's southwestern coast, a granite tower rises 35 meters above mean sea level. Constructed between 1862 and 1869, Wolf Rock Lighthouse was engineered to withstand Atlantic storm conditions that had destroyed previous structures on similar exposed sites. The tower's tapering profile, dovetailed stone construction, and foundation system represented the culmination of mid-Victorian lighthouse engineering. Every design parameter, from wall thickness gradations to stone interlocking mechanisms, was calculated to resist horizontal wave forces exceeding 400 kilonewtons per square meter. Yet the structure operated at the margins of engineering knowledge. The designers worked without theoretical frameworks for wave impact loads on emerged cylindrical structures. Foundation calculations relied on assumptions about rock masonry interface behavior under cyclic loading. The vertical key system that prevented sliding between stone courses was sized based on limited precedent rather than comprehensive analysis. Most critically, the entire structural concept depended on the assumption that maximum wave forces would act horizontally rather than creating complex uplift and rotational moments. The lighthouse functioned exactly as designed, but the design itself operated at the boundary between adequacy and failure. Every storm validated design assumptions that could not be fully proven until tested by the Atlantic itself. How can a structure succeed when its design operates beyond the limits of available engineering knowledge? The foundation of this analytical investigation lies in understanding that Wolf Rock Lighthouse represented an extrapolation of existing engineering principles into uncharted territory. When James Douglas assumed responsibility for the project in 1862, he inherited a design philosophy derived from John Smeaton's pioneering work at Eddystone nearly a century earlier. Smeaton's tapering masonry profile had proven successful, but Eddystone operated in fundamentally different conditions. The new site presented wave exposures that exceeded any previous lighthouse engineering challenge. The structural design philosophy centered on three core assumptions that would prove problematic under extreme conditions. First, the tapering circular profile was assumed to distribute wave forces predictably through the masonry structure, with maximum stresses occurring at the base where wall thickness was greatest. This assumption relied on simplified static load analysis that treated wave impacts as quasi-steady horizontal forces, rather than the complex dynamic phenomena they actually represented. The design calculations assumed wave forces would decrease linearly with height, following the tower's tapering geometry. Second, the foundation system assumed that adequate bearing capacity could be achieved through careful excavation and fitting of the granite base courses to the irregular rock surface. The designers believed that proper stone-to-rock contact would distribute foundation loads sufficiently to prevent overturning or settlement. This assumption neglected the possibility that wave-induced uplift forces and cyclic loading could create stress concentrations at contact points that exceeded local rock strength. Third, the dovetailed stone jointing system was designed on the premise that mechanical interlocking would prevent joint opening and maintain structural continuity under lateral loading. The vertical keys between horizontal courses were sized to resist sliding forces calculated from simplified horizontal wave pressure estimates. These calculations did not account for the complex stress states that would develop when the structure experienced simultaneous horizontal, vertical, and rotational forces during storm conditions. The structural analysis available to Victorian engineers was fundamentally inadequate for the loading conditions Wolf Rock would experience. Wave impact theory did not exist in any meaningful form. The designers relied on empirical observations from existing lighthouses, extrapolated to more severe conditions through engineering judgment rather than rigorous analysis. The Winke-Umarasi method for calculating breaking wave forces on vertical cylinders would not be developed for another 130 years, leaving designers to estimate loads based on hydrostatic pressure calculations that dramatically underestimated dynamic impact forces. The geometric constraints imposed by the site forced design compromises that operated at the margins of structural adequacy. The Wolf Rock Pinnacle provided a foundation area of approximately 200 square meters, with much of that surface being irregularly sloped. The usable foundation footprint was essentially circular with a diameter of approximately 12 meters, creating a height-to-base ratio that approached the limits of stability for masonry towers under lateral loading. This geometric constraint meant that overturning stability relied heavily on the self-weight of the structure and the assumption that the foundation would behave as a rigid, immovable base. The material selection and construction methodology embodied assumptions about granite behavior under cyclic loading that were not validated by available knowledge. The dovetail jointing system required precise stone cutting and fitting that was difficult to achieve under site conditions. Each stone course required individual fitting to accommodate the tapering geometry and irregular foundation surface. The quality of these joints was critical to structural performance, yet construction records indicate significant weather-related delays that forced work to proceed under marginal conditions. The structural calculations assumed that granite would behave essentially as an elastic material under service loading with adequate fatigue resistance for the anticipated loading cycles. This assumption ignored the reality that stone masonry structures develop complex internal stress patterns due to thermal effects, settlement, and load redistribution that can cause local stress concentrations exceeding the apparent design loads. The designers had no framework for analyzing fatigue failure in masonry joints subjected to millions of loading cycles over the structure's anticipated service life. Perhaps most critically, the instrumentation and monitoring capabilities available in the 1860s provided no means to verify whether the structure was performing as designed. The designers could observe that the lighthouse remained standing, but they had no way to measure actual stress levels, joint movements, or foundation settlements that might indicate the structure was operating closer to failure than anticipated. This information gap meant that design assumptions could not be validated or corrected based on operational experience. The vertical key system that prevented sliding between stone courses was designed based on simplified force calculations that assumed horizontally applied wave forces would create predictable shear stresses at the horizontal joints. The keys were sized to resist these calculated shear forces with an assumed factor of safety. However, this analysis neglected the possibility that uplift forces could reduce the normal stress across joints, dramatically reducing the effectiveness of friction in resisting sliding. Under such conditions, the vertical keys would carry loads far exceeding their design capacity. The wave loading assumptions embedded in the design reflected the best available knowledge of the 1860s, but this knowledge base was fundamentally inadequate for the extreme conditions Wolf Rock would encounter. The designers assumed wave forces could be calculated using hydrostatic pressure principles, treating waves as slowly varying water level changes rather than dynamic impact phenomena. The actual wave loading would involve breaking waves with approach velocities exceeding 20 meters per second, creating impact pressures that could reach several times the pressures used in design calculations. The foundation design assumed that careful excavation and stone fitting would create a monolithic connection between the tower and the underlying rock. This assumption neglected the reality that rock foundations are rarely homogeneous and that stress concentrations at contact points could exceed local rock strength. The irregular geometry of the Wolf Rock pinnacle meant that foundation loads would not be distributed uniformly, creating potential failure planes within the rock mass that were not considered in the design process. The structural continuity assumptions embedded in the dovetail joining system required that mechanical connections between stones would maintain their effectiveness under all anticipated loading conditions. This assumption was based on experience with similar construction in less severe environments, where the loading cycles were both less frequent and less severe than those anticipated at Wolf Rock. The designers could not anticipate that the cyclic nature of Atlantic storm loading would create fatigue conditions that could gradually degrade joint performance over time. The environmental assumptions underlying the design reflected incomplete understanding of the corrosive effects of marine exposure on both the granite stones and the metal elements used in construction. The vertical keys and other metal components were assumed to maintain their structural properties indefinitely, without consideration of corrosion effects that could reduce their load-carrying capacity over time. Similarly, the assumption that granite would maintain its mechanical properties under marine exposure neglected the possibility of surface degradation and joint deterioration that could affect long-term structural performance. These design assumptions created a structure that operated within acceptable parameters under normal conditions but had minimal reserve capacity for extreme events. The lighthouse was designed to survive anticipated loading, but it lacked the redundancy and conservatism that modern engineering practice would require for such extreme exposure conditions. The margin between design loads and actual capacity was narrower than the designers realized, creating conditions where relatively small increases in environmental loading or reductions in material capacity could threaten structural integrity. The construction of Wolf Rock Lighthouse embodied a fundamental contradiction between engineering requirements and operational reality. The project demanded precision stone fitting and foundation preparation that approached theoretical perfection. Yet these requirements had to be executed on an isolated Atlantic rock during brief weather windows that rarely exceeded 6 hours of workable conditions. This contradiction created latent conditions where the gap between design intent and achieved construction quality could remain permanently concealed within the structure itself. The construction methodology imposed by site conditions systematically compromised the verification processes that would normally ensure design compliance. James Douglas and his construction teams faced environmental constraints that made it impossible to achieve the construction quality assumed in structural calculations. Weather windows suitable for landing men and materials occurred unpredictably and lasted only as long as sea conditions remained below critical thresholds. These operational constraints forced construction decisions that prioritized immediate safety over long-term structural verification. The foundation preparation process revealed the first systematic divergence between design assumptions and construction reality. The design called for careful excavation of the rock surface to create uniform bearing conditions for the base courses of masonry. However, the irregular geometry of the Wolf Rock pinnacle meant that this excavation had to be performed by hand tools during brief landing opportunities, with no possibility of achieving the precise surface preparation that foundation calculations assumed. Construction records indicate that workers were often forced to accept approximations of design geometry when time and weather conditions prevented optimal preparation. The precision required for dovetailed stone fitting created another systematic source of construction compromise. Each stone had to be individually shaped and fitted to achieve the mechanical interlocking that the structural design required. The tolerances for these joints were measured in millimeters, yet the work had to be performed under conditions where tool precision was compromised by salt spray, temperature fluctuations, and time pressure. The quality control process that would normally verify joint fit and bearing contact was necessarily abbreviated due to the limited time available for each construction operation. The material delivery and storage constraints imposed by the site created additional opportunities for construction quality degradation. Stones were pre-shaped at the shore facility in Penzance, then transported to the site by barge and lifted into position using temporary cranes. This process subjected the precision-fitted stones to handling stresses and potential damage during transport and placement. Any damage to stone edges or bearing surfaces could compromise joint quality, but field repairs under site conditions were extremely limited in scope and effectiveness. The construction sequencing imposed by weather constraints forced deviations from optimal structural construction practices. The ideal construction sequence would have allowed each course of stones to be placed, verified, and properly bedded before proceeding to the next level. However, when weather windows allowed access to the site, construction crews were under pressure to place as many stones as possible before conditions deteriorated. This pressure created incentives to accept marginal joint fits and incomplete bearing contact rather than risk losing the opportunity to make progress. The quality verification processes that were standard practice in lighthouse construction had to be adapted to the extreme constraints of the Wolf Rock site. Normal practice called for systematic inspection of joint fits, bearing contacts, and foundation conditions before accepting each stage of construction. At Wolf Rock, such inspections were often performed under marginal conditions with limited time for corrective action. The construction supervisors were forced to make acceptability decisions based on visual inspection rather than the systematic verification that structural performance required. The communication constraints between the shore-based design team and the site construction crews created additional opportunities for construction quality degradation. Design modifications and construction guidance had to be communicated through written instructions that were prepared in advance of each construction operation. There was no opportunity for real-time consultation when site conditions, required deviations from planned procedures. Construction supervisors had to interpret design intent and make field decisions that could have permanent structural implications. The material handling equipment available in the 1860s imposed limitations on construction precision that were not fully accounted for in design calculations. The temporary cranes used for stone placement had limited positioning accuracy and load control compared to modern equipment. Stone placement operations required significant manual guidance and adjustment, creating opportunities for damage to precision-fitted joints during the final positioning process. The lifting equipment could not guarantee that stones would be placed exactly as designed, particularly under marginal weather conditions. The environmental conditions during construction created systematic stresses on both workers and equipment that compromised construction quality. Salt spray degraded tool performance and created slippery working conditions. Temperature fluctuations caused thermal expansion effects that could affect joint fits and tool calibration. Wind loads on lifting equipment reduced positioning accuracy and created safety hazards that forced conservative handling procedures. These environmental factors systematically degraded the precision that structural performance required. The foundation interface between the granite masonry and the irregular rock surface presented verification challenges that could not be fully resolved under site conditions. The design assumed that foundation stones could be fitted to achieve uniform bearing contact across their entire footprint. However, the irregular geometry of the rock surface and the limited time available for foundation preparation meant that bearing contact was necessarily approximate rather than precise. The actual contact area and stress distribution could not be verified without destructive testing that was incompatible with construction requirements. The vertical key installation process revealed systematic compromises between design intent and construction capability. The vertical keys that prevented sliding between stone courses required precise installation in pre-cut recesses to function as designed. However, the field cutting and fitting of these recesses had to be performed under marginal conditions, with limited time for precision work. The actual fit and load transfer capability of installed keys could not be verified without testing that would compromise their structural function. The mortar and bedding compound application processes were similarly compromised by environmental conditions. The design assumed that bedding materials would be applied under controlled conditions to achieve uniform thickness and complete contact. However, the marine environment and time constraints forced application under conditions where material performance could be degraded by temperature, humidity, and salt exposure. The quality of bedding layer installation could not be verified after stone placement without destructive examination. The construction inspection and acceptance criteria had to be adapted to acknowledge the limitations imposed by site conditions. Standard lighthouse construction practice called for systematic verification that each element met design specifications before proceeding to the next construction phase. At Wolf Rock, acceptance criteria necessarily focused on gross compliance rather than detailed verification. Construction elements that met minimum functional requirements were accepted even when they fell short of optimal design performance. The workforce capabilities and training represented another systematic constraint on construction quality. The extreme site conditions required workers with specialized skills in both stone construction and marine operations. The combination of these skill sets was rare, forcing reliance on workers whose expertise was stronger in one area than the other. Additionally, the physical demands and safety hazards of the site created high turnover rates that limited the development of specialized expertise for the unique requirements of the project. The tool and equipment limitations of 1860s construction technology created systematic constraints on construction precision. Stone cutting and fitting operations relied on manual tools whose performance was degraded by environmental conditions. Measurement and alignment equipment lacked the precision and environmental resistance that modern construction demands. Material handling equipment had limited capacity and positioning accuracy compared to contemporary standards. These technological limitations meant that construction quality necessarily fell short of theoretical requirements. The safety requirements that protected workers during construction operations created additional constraints on construction quality. Safety procedures necessarily took precedence over construction precision when the two requirements conflicted. Workers were required to prioritize personal safety over optimal construction practices, creating systematic tendencies toward expedient rather than optimal construction methods. The safety equipment and procedures available in the 1860s were primitive compared to modern standards, creating additional time pressure to complete operations during favorable conditions. The economic constraints imposed by the project funding and schedule created additional pressure for construction compromises. The project operated under fixed budget constraints that limited the time and resources available for construction quality optimization. Weather delays created cost pressures that incentivized accepting marginal construction quality rather than extending the construction schedule. The economic structure of the project created systematic biases toward minimum acceptable quality rather than optimal structural performance. These construction constraints created a structure whose actual performance characteristics differed systematically from design assumptions. The cumulative effect of thousands of small compromises in joint fits, bearing contacts, foundation preparation, and material installation created structural properties that could not be verified or quantified during construction. The lighthouse met minimum functional requirements, but its actual margin of safety was unknowable and potentially less than design calculations indicated. The winter storms of the 1870s provided the first empirical data about Wolf Rock Lighthouse's actual structural performance under extreme loading conditions. During these early operational years, the structure experienced wave conditions that began to reveal the gap between design assumptions and physical reality. The lighthouse remained functional, but observers noted structural responses that had not been anticipated in design calculations. These observations marked the beginning of a divergence between theoretical performance and measured behavior that would persist throughout the structure's operational life. The Atlantic storm season of 1874 produced wave conditions that exceeded the design parameters used in structural calculations. Contemporary accounts describe waves that completely engulfed the lighthouse lantern, indicating wave heights approaching 50 meters above mean sea level. These conditions created loading patterns that were fundamentally different from the quasi-static horizontal forces assumed in design calculations. Instead of the predictable pressure distributions that structural analysis anticipated, the lighthouse experienced complex dynamic loading that included simultaneous horizontal impact, vertical uplift, and rotational moments. The structural monitoring capabilities available during the lighthouse's early operational period were limited to visual observation and gross functionality assessment. Trinity House personnel could verify that the lighthouse continued to operate and that no obvious structural damage had occurred, but they had no means to measure the actual stresses, deflections, or joint movements that would indicate how closely the structure was operating to its design limits. This monitoring limitation meant that potentially significant structural responses remained undetected and unquantified. The first systematic observations of unexpected structural behavior occurred during the severe storm conditions of December 1876. Lighthouse keepers reported structural vibrations and movements that were perceptible inside the tower, but did not correspond to any anticipated design behavior. The lighthouse was not designed to have perceptible dynamic response under wave loading, yet occupants could feel the structure's response to major wave impacts. These observations suggested that the actual structural stiffness and damping characteristics differed from design assumptions. The wave impact phenomena observed during extreme storms revealed loading patterns that were not considered in design calculations. Rather than the steady pressure distributions that structural analysis assumed, wave impacts created impulsive loading that lasted only a few seconds but generated forces significantly exceeding design values. The breaking wave impacts produced shock loading that propagated through the structure as stress waves, creating internal force distributions that were fundamentally different from static analysis predictions. The foundation response during extreme loading conditions provided the first evidence that the rock structure interface was behaving differently than design assumptions anticipated. Observers noted that the lighthouse exhibited slight but perceptible movement during major wave impacts, suggesting that the foundation was not behaving as the rigid support that structural calculations assumed. These movements indicated that either the rock was deforming under load, or that the interface between the masonry and rock was not as rigid as designed. the dovetailed joint system began showing evidence of behavior that was not anticipated in structural design. During extreme loading events, lighthouse keepers reported hearing sounds that suggested relative movement between stone courses. These observations indicated that the joints were experiencing loading patterns that caused them to behave differently than the rigid connections that structural analysis assumed. The actual joint behavior appeared to involve some degree of flexibility that allowed relative movement between structural elements. The material performance observations during the first decade of operation revealed environmental effects that were not considered in design calculations. The granite stones showed evidence of surface deterioration due to salt spray and thermal cycling that was more severe than anticipated. The metal components, particularly the vertical keys and iron reinforcements, showed corrosion effects that were accelerating faster than expected. These material degradation effects suggested that the long-term structural capacity might decrease more rapidly than design assumptions anticipated. The wave loading measurements that became possible during the 1880s revealed that actual wave forces were significantly different from design calculations. When systematic wave observation began, it became clear that the breaking wave impacts on the lighthouse involved much higher instantaneous forces than the hydrostatic pressure calculations used in design. The dynamic amplification effects of wave impacts created loading conditions that exceeded design parameters by factors that ranged from 2 to 5 times the calculated values. The structural response measurements that became available through improved instrumentation revealed dynamic characteristics that were not anticipated in design. The lighthouse exhibited natural frequencies and dynamic amplification effects that suggested the structure was more flexible than rigid analysis had predicted. This flexibility meant that dynamic loading could create structural responses that were significantly different from static analysis predictions, particularly during resonant conditions when wave frequencies approached the structure's natural frequency. The Foundation's settlement monitoring that began during the 1880s revealed that the rock structure interface was experiencing gradual changes that were not anticipated in design. Systematic measurements showed that the lighthouse was experiencing small but measurable settlement and tilting that suggested the foundation was not behaving as a rigid support. These movements were small enough that they did not affect structural function, but they indicated that the foundation design assumptions were not accurate representations of actual behavior. The joint performance monitoring revealed that the dovetailed stone connections were experiencing loading patterns that caused gradual degradation of their mechanical properties. Visual inspection of accessible joints showed evidence of movement and wear that indicated the joints were accommodating structural deformations that exceeded design expectations. The actual joint behavior suggested that the rigid connection assumption used in structural analysis was not accurate for the loading conditions the lighthouse experienced. The thermal effects observation during extreme weather conditions revealed structural responses that were not considered in design calculations. The massive granite construction created thermal inertia effects that caused significant internal stresses during rapid temperature changes associated with storm passage. These thermal stresses combined with wave loading to create stress patterns that were more complex than structural analysis had anticipated. The thermal effects were particularly significant during winter storms when air temperatures dropped rapidly while wave action continued. The environmental loading effects beyond wave impact began to reveal additional structural challenges that were not anticipated in design. Wind loading during extreme storms created additional lateral forces that combined with wave loading to increase total structural loads beyond design parameters. The wind effects were particularly significant when storm conditions created sustained high winds that persisted between wave impacts, creating steady loading that added to the impulsive wave forces. The operational loading effects created by lighthouse function and maintenance activities revealed that the structure was experiencing service loads that were not considered in design calculations. The movement of personnel and equipment within the tower created dynamic loading that combined with environmental effects to increase total structural stress. The vibration and impact associated with lighthouse operation created fatigue loading cycles that were additional to the environmental fatigue caused by wave action. The material degradation monitoring revealed that environmental exposure was affecting structural capacity in ways that were not anticipated during design. The granite stones were experiencing surface deterioration that reduced their effective bearing area and altered load distribution patterns. The mortar and bedding compounds were deteriorating at rates that were faster than anticipated, creating the potential for load redistribution that could increase stresses in remaining structural elements. The structural performance under extreme loading revealed safety margins that were narrower than design calculations had indicated. The observable structural responses during major storms suggested that the lighthouse was operating closer to its capacity limits than originally understood. While the structure remained functional, the margin between operational loads and structural failure appeared to be less than the safety factors that structural calculations had assumed. The cumulative effects of repeated extreme loading began to reveal structural changes that suggested fatigue damage accumulation. The lighthouse was experiencing millions of loading cycles due to wave action, and the cumulative effects of this cyclic loading were causing gradual changes in structural properties. The fatigue effects were most apparent in the joint systems, where repeated loading was causing gradual degradation of the mechanical connections that structural continuity required. These early operational observations established that Wolf Rock Lighthouse was performing differently than design calculations predicted across multiple performance parameters. The structure remained functional, but its actual behavior under extreme loading suggested that design assumptions about loading patterns, structural response, foundation behavior, and material performance were systematically optimistic. The lighthouse was operating with safety margins that were narrower than originally calculated, creating conditions where continued structural adequacy depended on conservative factors that had not been explicitly considered in design. The physical reality of extreme wave loading on Wolf Rock Lighthouse involved complex, fluid structure interaction phenomena that were fundamentally beyond the analytical capabilities of Victorian engineering. When Atlantic storms generated breaking waves that exceeded 40 meters in height, the lighthouse experienced loading patterns that bore little resemblance to the hydrostatic pressure distributions used in design calculations. The actual physics of wave structure interaction created force patterns that challenged every assumption underlying the structural design, revealing the extent to which the engineering approach of the 1860s was inadequate for the extreme conditions the lighthouse would encounter. The wave impact sequence during extreme storms involved multiple loading phases that each created distinct structural challenges. The initial wave approach created a pressure buildup phase as the wave mass decelerated against the lighthouse structure. This pressure buildup created loading patterns that were distributed over the impact area according to wave geometry rather than the uniform pressure distributions that structural calculations assumed. The pressure magnitude during this phase could exceed design calculations by factors of 3 to 5, creating structural stresses that approached or exceeded design capacity limits. The breaking wave impact phase generated impulsive loading that was fundamentally different from any loading condition considered in structural design. When waves broke against the lighthouse, they created shock loads that lasted only milliseconds but generated instantaneous pressures exceeding 500 kilopascals. These impulsive loads propagated through the masonry structure as stress waves, creating internal force distributions that were completely different from static analysis predictions. The stress wave propagation caused localized stress concentrations at geometry changes and material interfaces that could exceed local material capacity, even when overall structural loads remained within design limits. The wave run-up phase created vertical loading patterns that were not considered in structural calculations. After impact, wave water traveled up the lighthouse surface, creating additional pressure distributions that varied with height and time. During extreme events, wave run-up could reach the lighthouse lantern level, creating vertical pressure distributions that extended over the entire structure height. These pressure distributions created overturning moments that exceeded the stabilizing moments calculated from horizontal wave pressure alone. The wave withdrawal phase generated negative pressure effects that created structural loading patterns opposite to those considered in design. As wave water retreated from the lighthouse, it created suction effects that could generate uplift forces on structural elements. These uplift forces were particularly significant for elements such as gallery platforms and external fixtures that had been designed only for downward loading. The combination of positive impact pressure followed immediately by negative withdrawal pressure created stress reversals that doubled the effective loading cycles for fatigue analysis. The dovetailed joint system experienced loading patterns that revealed fundamental inadequacies in the mechanical design assumptions. Under extreme wave loading, the joints experienced combined tension, compression, and shear forces that created stress states not considered in design calculations. The dovetailed geometry that was intended to prevent joint separation actually created stress concentrations that amplified local stresses beyond material capacity. When joints experienced uplift forces, the dovetailed connections created wedging effects that could split individual stones or cause progressive joint failure. The vertical key system, that was designed to prevent sliding between stone courses, experienced loading conditions that exceeded its capacity to function as designed. During extreme wave events, the combination of horizontal and vertical forces created loading patterns that reduced the normal stress across horizontal joints while simultaneously increasing the shear stress that the keys had to resist. Under these conditions, the vertical keys carried loads that could exceed their material capacity, creating the potential for progressive failure that could propagate through multiple stone courses. The foundation superstructure interface experienced stress transfer mechanisms that were fundamentally different from the uniform, bearing stress distribution that design calculations assumed. The irregular geometry of the rock foundation created contact stress concentrations that could exceed local rock capacity even when overall foundation loads remained within design limits. The rock foundation exhibited local deformation under extreme loading that created stress redistribution patterns within the masonry structure. These stress redistributions could create secondary loading patterns that exceeded design capacity in areas that were not identified as critical during original analysis. The material behavior under extreme loading revealed failure mechanisms that were not considered in structural design. The granite stones experienced stress levels that approached their tensile capacity during extreme loading events. The cyclic nature of wave loading created fatigue conditions that could cause crack initiation and propagation in individual stones, even when stress levels remained below ultimate material capacity. The crack propagation patterns followed the internal grain structure of the granite, rather than the external geometry that structural analysis assumed, creating failure modes that were difficult to predict or prevent. The stress concentration effects of geometry transitions created localized failure mechanisms that could initiate catastrophic structural failure. The transitions between different wall thicknesses, the connections between the lighthouse tower and foundation, and the interfaces between stone courses all created stress concentration factors that amplified local stresses beyond design calculations. These stress concentrations were particularly severe during impulsive wave loading when stress wave propagation created dynamic amplification effects that could increase local stresses by factors of 2 to 3 times static values. The thermal stress effects during extreme weather conditions combined with wave loading to create stress patterns that exceeded design capacity. The massive masonry construction created thermal gradients during rapid temperature changes that generated internal stresses independent of external loading. When thermal stresses combined with extreme wave loading, the resulting stress patterns could exceed material capacity even when individual loading components remained within design limits. The thermal effects were particularly critical during winter storms when rapid cooling combined with maximum wave loading. The dynamic amplification effects revealed that the lighthouse structure had natural frequencies that could create resonant response under certain wave loading conditions. When wave impact frequencies approached the structure's natural frequency, dynamic amplification could increase structural response by factors that exceeded the static analysis safety margins. The resonant conditions occurred unpredictably depending on wave characteristics and structural properties, creating loading conditions that could not be anticipated or controlled through design modifications. The progressive failure mechanisms that became apparent under extreme loading revealed that structural failure could occur through mechanisms that bypass the primary load-carrying systems. Joint degradation could redistribute loads, to create failure patterns that propagated through the structure in ways that were not anticipated in design analysis. The interdependence of structural elements meant that failure of secondary components could trigger redistributions that overloaded primary structural elements, creating cascading failure modes that were not considered in design. The material fatigue effects under millions of loading cycles created structural degradation that reduced capacity below design values over time. The cyclic loading caused crack initiation and propagation in both stone and mortar elements that gradually reduced effective cross-sectional area and altered load distribution patterns. The fatigue effects were cumulative and irreversible, meaning that structural capacity decreased continuously throughout the operational life of the lighthouse. The rate of capacity reduction was not predictable from design analysis because the actual loading patterns differed systematically from design assumptions. The environmental degradation effects accelerated structural capacity reduction beyond the rates anticipated during design. Salt spray exposure caused chemical attacks on both stone and metal elements that reduced material properties faster than design life calculations anticipated. The combination of mechanical loading and chemical degradation created synergistic effects that accelerated structural deterioration beyond the sum of individual effects. These synergistic effects were particularly severe at stress concentration locations, where mechanical damage provided pathways for accelerated chemical attack. The load redistribution effects caused by localized failure created loading patterns that differed fundamentally from original design assumptions. As individual structural elements experienced damage or capacity reduction, loads redistributed to adjacent elements in patterns that were not anticipated in design calculations. The load redistribution could create overloading conditions in elements that were originally designed for lower stress levels, creating the potential for progressive failure that could compromise overall structural integrity. The actual safety margins under extreme loading proved to be significantly less than design calculations indicated. The combination of higher actual loads, lower actual capacity, and degradation effects over time meant that the lighthouse operated closer to failure conditions than originally understood. The structure remained functional because of conservative material factors and beneficial load distribution effects that were not explicitly considered in design, but the actual safety margin was narrower than the factors of safety that design calculations assumed. These physical reality checks revealed that Wolf Rock Lighthouse survived extreme loading conditions through a combination of conservative material selection, beneficial geometric effects, and operational factors that were not captured in design analysis. The structure's survival validated the basic design approach while simultaneously revealing the inadequacy of the analytical methods used to determine design parameters. The lighthouse operated successfully at the margins of engineering knowledge, demonstrating both the limits of Victorian structural analysis and the importance of conservative design factors when analytical understanding is incomplete. The recognition that Wolf Rock Lighthouse was operating outside its design parameters triggered a series of intervention attempts that revealed the complexity of maintaining structural integrity when the original design assumptions proved inadequate. Trinity House faced the challenge of stabilizing a structure that was experiencing loading conditions beyond its design capacity, while simultaneously lacking the analytical tools to quantify the actual safety margins or predict the effectiveness of proposed modifications. Each intervention attempt provided new information about structural behavior while creating additional uncertainties about long-term performance. The first systematic intervention occurred during the 1880s, when Trinity House implemented a comprehensive inspection and monitoring program to assess the lighthouse's condition after 2 decades of operation under extreme conditions. This program revealed that the structure was experiencing gradual changes that indicated ongoing structural stress beyond design levels. Visual inspection of accessible joints showed evidence of movement and wear patterns that suggested the dovetailed connections were accommodating deformations not anticipated in original calculations. The monitoring data indicated that the lighthouse was adapting to loading conditions through mechanisms that were not part of the original structural design. The foundation monitoring program revealed settlement and tilting patterns that indicated the rock structure interface was behaving differently than the rigid connection that design calculations assumed. Systematic measurements showed that the lighthouse was experiencing differential settlement that created internal stress redistributions within the masonry structure. The settlement patterns were small in absolute terms but significant relative to the precision required for optimal structural performance. These foundation movements created secondary loading patterns that combined with environmental loading to increase total structural stress beyond design capacity. The joint reinforcement program implemented during the 1890s represented the first major structural intervention based on observed performance deficiencies. Trinity House engineers recognized that the dovetailed joint system was experiencing loading patterns that exceeded its design capacity and implemented supplementary restraint systems to provide additional resistance to joint separation and sliding. However, the reinforcement design was necessarily based on limited understanding of actual loading patterns and joint behavior, creating uncertainty about whether the interventions would provide adequate improvement in structural performance. The installation of external monitoring equipment during the early 1900s provided the first systematic data about actual structural response under extreme loading. Strain gauges and deflection measurements revealed that the lighthouse was experiencing deformations that exceeded the rigid body assumptions used in original structural analysis. The monitoring data showed that the structure had significant flexibility that allowed it to accommodate extreme loading through deformation rather than pure strength resistance. This flexibility was beneficial for survival under impulsive loading, but indicated that the structure was operating in a deformation range that exceeded design assumptions. The material replacement program that began during the early 20th century revealed the extent to which environmental degradation was reducing structural capacity below design values. The replacement of deteriorated stones and corroded metal elements showed that capacity reduction was occurring faster than anticipated during design. The pattern of material deterioration indicated that environmental loading was creating stress concentrations and damage accumulation that accelerated degradation beyond normal weathering effects. The material replacement program provided temporary capacity restoration, but did not address the underlying causes of accelerated degradation. The structural modification program implemented during the 1920s represented the most significant intervention in the lighthouse's operational history. This program included foundation reinforcement, joint system upgrades, and the installation of additional structural restraints to improve resistance to extreme loading. However, the modifications were necessarily based on limited analytical understanding of actual structural behavior and loading patterns. The intervention design relied heavily on engineering judgment and conservative factors rather than rigorous analysis of load paths and capacity requirements. The monitoring of intervention effectiveness revealed that structural modifications could create unintended consequences that affected overall performance in unpredictable ways. The addition of reinforcement elements altered load distribution patterns within the existing structure, creating new stress concentration locations that had not been anticipated. The modified structure exhibited different dynamic characteristics that could affect response to extreme loading in ways that were not fully predictable from the analysis methods available at the time. The development of improved monitoring capabilities during the mid-20th century provided new insights into structural behavior that revealed both the effectiveness and limitations of previous interventions. Advanced instrumentation showed that the lighthouse was continuing to experience loading patterns and structural responses that exceeded the assumptions underlying both original design and subsequent modifications. The improved monitoring revealed that structural behavior was more complex than previous analysis methods could capture, with load paths and response mechanisms that involved the entire structure rather than discrete structural elements. The long-term performance monitoring revealed that the lighthouse was experiencing gradual structural changes that indicated ongoing adaptation to loading conditions beyond design capacity. The structure was developing internal stress redistributions and deformation patterns that allowed it to survive extreme loading while simultaneously indicating that it was operating outside its original design envelope. These adaptive mechanisms were beneficial for short-term survival, but created uncertainty about long-term structural integrity and the potential for sudden capacity reduction. The intervention program evaluation revealed that many of the implemented modifications provided local improvements in structural performance. while creating system-level uncertainties about overall behavior. The reinforcement of individual structural elements could improve local capacity while altering load distribution patterns in ways that increase stress levels in other areas. The cumulative effect of multiple interventions created a structure whose behavior was increasingly different from original design assumptions and difficult to predict using available analytical methods. The development of modern structural analysis methods during the latter half of the 20th century provided new tools for evaluating lighthouse performance, but also revealed the extent to which previous interventions had been based on inadequate understanding of actual structural behavior. Advanced finite element analysis showed that the lighthouse was experiencing stress patterns and load distributions that were fundamentally different from the assumptions underlying both original design and subsequent modifications. The modern analysis revealed that the structure's survival was due to factors that had not been explicitly considered in any previous analysis. The materials testing program implemented during the 1980s revealed that the lighthouse's granite and construction materials had properties that differed from the assumptions used in both original design and subsequent intervention design. The actual material properties were generally more conservative than design assumptions, providing additional capacity margins that partially compensated for the higher actual loading conditions. However, the material testing also revealed degradation patterns and property variations that created additional uncertainties about structural capacity and performance predictability. The seismic analysis program revealed additional loading conditions that had not been considered in original design or subsequent interventions. While seismic loading was not a primary concern for the lighthouse's location, the analysis revealed that the structure's dynamic characteristics made it potentially vulnerable to resonant excitation from sources other than wave loading. The seismic analysis provided insights into structural behavior that were relevant to understanding response to all types of dynamic loading, including extreme wave impacts. The environmental monitoring program revealed that the lighthouse was experiencing environmental conditions that exceeded the severity assumptions used in original design and subsequent intervention planning. The marine environment was causing material degradation rates that were faster than anticipated, while climate change was increasing the frequency and severity of extreme storm conditions. The environmental monitoring indicated that the challenge of maintaining structural integrity was increasing over time due to changes in both loading conditions and material properties. The intervention cost-benefit analysis revealed that maintaining the lighthouse within acceptable safety margins required ongoing investment in monitoring, maintenance, and structural modifications that exceeded the cost assumptions used in original project planning. The economic analysis showed that the true cost of operating a structure at the margins of engineering knowledge included not only construction and normal maintenance costs, but also the substantial ongoing investment required to monitor performance and implement modifications. As understanding of structural behavior evolved, the risk assessment analysis revealed that the lighthouse was operating with safety margins that were narrower than modern engineering practice would accept for similar structures. The combination of higher actual loads, material degradation effects, and analytical uncertainties created risk levels that exceeded acceptable thresholds for critical infrastructure. The risk analysis indicated that continued operation required acceptance of uncertainties about structural performance that were incompatible with modern safety standards. These stabilization attempts revealed that maintaining structural integrity when operating beyond design limits required continuous adaptation of both the structure itself and the analytical methods used to evaluate its performance. The lighthouse's survival demonstrated the importance of conservative design factors and the value of ongoing monitoring and intervention programs, while simultaneously revealing the limitations of engineering methods when applied to extreme conditions beyond their validated range of applicability. The forensic evidence accumulated over 150 years of Wolf Rock Lighthouse operation provides a comprehensive record of how Victorian engineering performed when pushed beyond the limits of contemporary analytical knowledge. Modern structural assessment techniques, applied to evaluate the lighthouse's actual condition and performance, reveal systematic discrepancies between original design assumptions and measured structural behavior. These findings illuminate not only the specific technical inadequacies of 1860s lighthouse engineering, but also the broader implications of designing critical infrastructure when analytical understanding is incomplete. The comprehensive structural inspection conducted during the 1990s using advanced non-destructive testing methods provided the first definitive assessment of the lighthouse's actual condition compared to design predictions. Ground-penetrating radar revealed foundation interface conditions that differed significantly from the uniform bearing contact that structural calculations assumed. The radar data showed that effective bearing contact covered approximately 60% of the design footprint, with stress concentrations at contact points that exceeded design values by factors of 2 to 3. This finding explained the settlement and tilting patterns observed during earlier monitoring programs and confirmed that foundation design assumptions had been systematically optimistic. The ultrasonic testing of stone integrity revealed internal crack patterns that indicated stress levels had exceeded design assumptions during the lighthouse's operational history. The crack mapping showed that maximum stress concentrations occurred at locations that were not identified as critical during original structural analysis. The crack patterns followed the internal grain structure of the granite stones, rather than the external geometry assumed in design calculations, indicating that material behavior was more complex than Victorian engineering methods could analyze. The extent of internal cracking suggested that the lighthouse had survived loading conditions that approached or exceeded ultimate material capacity. The finite element analysis conducted using modern computational methods revealed stress distributions and load paths that were fundamentally different from the assumptions underlying original design calculations. The advanced analysis showed that the lighthouse's actual behavior under extreme loading involved complex, three-dimensional stress patterns that could not be captured by the simplified analytical methods available in the 1860s. The load paths identified by finite element analysis showed that structural continuity depended on mechanisms that were not explicitly considered in original design, including arch action effects and load redistribution through the dovetail joint system. The dynamic analysis using modern vibration testing revealed natural frequencies and mode shapes that confirmed the lighthouse had significant flexibility that was not accounted for in original rigid body analysis. The measured dynamic characteristics explained the perceptible structural response that lighthouse keepers had reported during extreme storms, and confirmed that the structure's survival under impulsive wave loading was partially due to its ability to deform and dissipate energy, rather than resist loading through pure strength. The dynamic analysis also revealed resonant frequencies that could create amplified response under certain wave loading conditions. The materials analysis using modern laboratory testing methods revealed granite properties that differed from the assumptions used in Victorian structural calculations. The actual compressive strength of the granite was approximately 20% higher than design assumptions, providing additional capacity margin that partially compensated for the higher actual loading conditions. However, the tensile strength was lower than assumed, and the fatigue resistance was significantly less than Victorian engineers had estimated. The materials analysis confirmed that structural survival had depended on the conservative nature of actual material properties in compression while revealing vulnerabilities in tension and fatigue that had not been adequately considered. The joint performance analysis using photogrammetric survey techniques revealed movement patterns that confirmed the dovetail joint system was accommodating deformations beyond design limits. The joint monitoring showed that individual joints were experiencing opening and sliding movements measured in millimeters, indicating that the rigid connection assumption used in structural analysis was not accurate. The joint movement patterns were reversible under normal loading conditions, but showed permanent deformation accumulation over time that indicated gradual degradation of joint performance. The foundation stability analysis using modern geotechnical methods revealed that the rock foundation had localized strength variations that created stress concentration effects not considered in original design. The geotechnical analysis showed that bearing capacity was limited by local rock strength rather than overall foundation size, confirming that stress concentrations at contact points exceeded local capacity during extreme loading events. The foundation analysis explained the differential settlement patterns observed during monitoring and confirmed that foundation design assumptions had not adequately considered the heterogeneous nature of the rock foundation. The wave loading analysis using modern coastal engineering methods revealed that actual wave forces on the lighthouse exceeded design calculations by factors that ranged from 3 to 8, depending on storm intensity and wave characteristics. The modern analysis confirmed that Victorian hydrostatic pressure calculations systematically underestimated the dynamic impact forces associated with breaking waves. The wave loading analysis also revealed that impulsive loading duration and pressure distribution patterns were fundamentally different from design assumptions, creating loading conditions that challenged every aspect of the structural design. The fatigue analysis using modern damage accumulation methods revealed that the lighthouse had experienced loading cycles that exceeded the fatigue capacity assumed in original design calculations. The fatigue analysis showed that millions of wave loading cycles had created cumulative damage that reduced structural capacity below design values over time. The fatigue effects were most significant in the joint systems and at stress concentration locations, where repeated loading had caused crack initiation and propagation that gradually reduced effective load-carrying capacity. The environmental degradation analysis revealed that marine exposure had created material property changes that were more severe than anticipated during design. Chemical analysis of granite samples showed mineral alterations and surface degradation that reduced material strength and altered load transfer mechanisms. The corrosion analysis of metal components revealed capacity reductions that exceeded design life predictions, confirming that environmental effects had been underestimated in original calculations. The degradation analysis showed that actual service life was shorter than design assumptions due to accelerated environmental effects. The structural system analysis using modern reliability methods revealed that the lighthouse's safety margin was significantly less than the factors of safety assumed in original calculations. The reliability analysis showed that the combination of higher actual loads, lower actual capacity, and degradation effects created failure probabilities that exceeded acceptable levels for critical infrastructure. The system analysis confirmed that structural survival had depended on beneficial factors that were not explicitly considered in design, including load redistribution effects and material property variations that provided additional capacity margins. The comparative analysis with similar structures revealed that Wolf Rock Lighthouse represented an extreme case of engineering at the limits of analytical knowledge. Comparison with other rock lighthouses showed that Wolf Rock experienced more severe loading conditions and exhibited greater structural response than structures designed using similar methods for less extreme environments. The comparative analysis confirmed that Wolf Rock pushed Victorian engineering methods beyond their validated range of applicability, creating conditions where design adequacy could not be verified until tested by operational experience. The modern design analysis revealed that current engineering methods would produce a significantly different structure for the same site conditions and performance requirements. Modern analysis methods would identify loading patterns, stress concentrations, and failure mechanisms that were not considered in Victorian design. The modern design would require larger foundations, different structural systems, and more conservative material factors to achieve acceptable safety margins under the actual loading conditions that Wolf Rock experiences. The design comparison confirmed that Victorian engineering methods were inadequate for the extreme conditions represented by the Wolf Rock site. The lessons learned analysis revealed systematic patterns of analytical inadequacy that extended beyond the specific technical limitations of Victorian engineering methods. The Wolf Rock experience demonstrated the dangers of extrapolating design methods beyond their validated range, the importance of conservative factors when analytical understanding is incomplete, and the value of ongoing monitoring and intervention when structures operate at the margins of engineering knowledge. These lessons remain relevant for modern engineering when dealing with extreme conditions or novel structural challenges where analytical understanding may be incomplete. The long-term performance analysis revealed that structures designed at the limits of engineering knowledge require fundamentally different approaches to safety assurance than structures designed well within established analytical capabilities. The Wolf Rock experience showed that such structures require ongoing monitoring, adaptive management, and acceptance of uncertainties that are incompatible with conventional engineering approaches. The performance analysis confirmed that engineering at the margins of knowledge requires explicit acknowledgement of analytical limitations and implementation of risk management strategies that account for unknown unknowns. These forensic findings confirm that Wolf Rock Lighthouse succeeded not because Victorian engineering methods were adequate for the conditions it faced, but because conservative material selection, beneficial structural characteristics, and ongoing adaptive management compensated for fundamental analytical inadequacies. The Lighthouse's survival validated the importance of engineering judgment and conservative factors when analytical understanding is incomplete, while simultaneously demonstrating the limitations of design methods when applied beyond their validated range of applicability.